I'm Jenny Seifert. I am the science writer and outreach coordinator for the Water Sustainability and Climate Project. I'm the one who's been sending you all the emails. So welcome. And I'm joined here by members of the research team. There's Eric Booth at this table, raise your hand. Chris Kucharik, Adena Rissman, Missy Motew, and then Steve Carpenter is going to be joining us a little late, and then Carly Zitter is somewhere here too. So that's who's here represented, and we're gonna skip over introducing or having you all introduce yourselves just in the to save some time. You'll have opportunities to introduce yourselves in our small groups later. And so the reason that we have convened you all here today is because you all work directly in land and water management, policy, or research, either here in the Yahara or statewide. And we felt that because of the work that you do, we wanted to share the work that we're doing in an effort to have a conversation around it. And so while our work is focused on the Yahara watershed, it certainly has implications statewide, which is why we're not focused on solely just the Yahara. So this is in your agenda, but the reasons that we have convened you here today are, to share our learning from our model results and regarding sort of vulnerabilities and opportunities to water sustainability in the Yahara and beyond, to generate discussion about what those results mean for the work that we're doing, to align our understanding about how models can best be used to inform policy and management, and finally to strengthen bridges between the research and the practitioner community. And along those lines, there are what we all have in common is our work, but we're all coming from different sectors and from different organizations. And so we have sort of a broad variety of backgrounds here. And specifically, there's sort of a broad variety of technical expertise in the room. And so as such, we try to design our conversation and our presentation to be tailored towards both the more technical and non-technical audience. So with that in mind, we're going to be taking a pretty broad perspective on the technical aspects of what our research is all about, and we're going to sort of save the really nitty-gritty technical details for another conversation. And so if technical conversations or a question for you arises, you might have the opportunity to address that question in one of our discussion groups, which will be focused on the more technical details, or we can put that question on the woodpile, which I will introduce, which is our place to put questions that might not be we have time to answer today or might require a whole new conversation. So we'll keep the woodpile in mind for any questions that arise along those lines. And so what we hope to have by the end of our discussion today is a list of potential solutions to sustaining water quality and other natural benefits based on our new insights. And this can be either totally new ideas or reinforcing ideas that we already have out there. An understanding of what you all would like to see stimulated in other modeling efforts. And then finally, some ideas for how scientific evidence like these model results can best be used in policy and management. And so before I hand the mic over to our presenters, I'm just going to sort of work to put your minds in the right frame for what we're talking about today. I think that when we think about our future water needs, we're not talking just about the quality of our lakes and rivers. We're talking about a whole suite of things that our watersheds provide us. We expect a lot from our watersheds and from our landscapes, and these benefits are not working in a vacuum. They're all interconnected, and so thinking about our whole watershed in that holistic way is really helpful, and probably something you already do. But I always find it really helpful to go back to that frame of mind. And along those lines, in terms of when we're thinking about how to sustain those benefits long into the future, we need to ask ourselves, and this is the question that the WSC project has been focused on for the past 6 years, is how could changes in land use, climate, and human demand impact those benefits into the future? And if we have an understanding of that, we can have a better understanding of how to build resilience for the region. And a simpler way of sort of asking this question is, can we have clean lakes and ice cream too? And thinking about, these guys and when they're our age, what will the lakes and what will agriculture be like, and of the other benefits in this region, how will those be meeting their needs? We're not, of course, focused on just water quality and agriculture. There's a lot of different needs, but I think this question is a really interesting way to think about this problem that we're all here to talk about. And to think about this question, we really need to take the long view. For those who have seen a presentation about Yahara 2070 before, you've heard us already talk about the need for the long view. Again, this is just sort of to help frame your mind about the conversation we're having today. We're thinking about 2 generations from now, which is not a typical time horizon for policy and management. And so we're taking a really big picture perspective to really help us explore that realm of uncertainty in the future and what these changes might mean. But 2 generations is also still not too long away that we don't feel connected to it. Some of the long-term changes affecting the Yahara watershed, you probably all know about this already, but just to again frame your mind, thinking about intensification of dairy agriculture, increasing demand for biofuels, urban development, and changes in climate. And so in thinking about and taking the long view, we're thinking about these changes that happen over the course of decades and create a lot of uncertainty because of the slow nature of the change. Another way to think about taking the long view is sort of recognizing that the choices that we make today do matter. Despite the uncertainty that these changes could bring us, we have the ability to make some choices today that can shape the future. And this is where scenarios come in some of our work, and they help us really think about these long-term changes and what challenges they might bring us and what that means for our choices today. So scenarios, just to review, they are provocative, plausible stories about the future with contrasting social and environmental conditions. And they help us explore uncertainty by asking that question, what if? They help us think about the long term and also thinking about multiple scales, so from not just our watershed here, but also throughout the state and throughout the globe. And finally, they help us learn ways to address change and build resilience. And so Yahara 2070, again, are our what-ifs for the future of water and people in the Yahara watershed. They're really meant to help us explore these long-term changes that are affecting the region and try to think about what is possible and also what is desirable and undesirable and how we might address those desirables and undesirables. And the scenarios are accompanied by what we're going to be focusing on today, and those are our models. Our models simulated the scenarios, and what they gave us is a range of plausible futures for the natural benefits that future generations will be depending on, so our ecosystem services that you see listed here. And together, these scenarios and the simulations and the model results sort of give us implications for the future of human well-being. And with an understanding of what's possible for future human well-being, we can think about, again, what is desirable and undesirable and what that means for our choices today. And just to remind you, the scenarios and the model results that are based on the scenarios, none of them are a worst case or a best case scenario, and there are no business as usual scenarios. We were really thinking outside the box in order to explore a really broad range of plausibility, so just to keep that in mind. So without further ado, before I hand over the mic, this is a question that is sort of going to orient our conversation today, and I want you to keep this in mind. And that's, given what we learned and discussed today, what priorities stand out and seem ripe for moving forward? And we're going to come back to this question at the end of our discussion. So I'm going to hand over to Eric Booth.
All right. Thank you, Jenny. Hi, everyone. I'm Eric Booth. I am a scientist here at UW-Madison in agronomy and civil and environmental engineering. I think I know almost all of you, but thank you for coming again and making time in your busy schedules to join us today. I am tasked with giving a very broad overview of the model results, all those different ecosystem services that Jenny mentioned. And before I get into the details, I just want to make sure everyone's aware that this project was funded by the National Science Foundation, and it was led by many great students and staff and faculty here at UW-Madison. In the last 5 or 6 years, we've had a great ride. just to put our modeling into a little bit of context, I want to start out with just what are environmental models doing for us in the Yahara watershed today, and this could be extended throughout the state. And a couple of models come to mind that you might be familiar with or have heard of at least. The first one being SNAP Plus. So this is a nutrient management model often used by farmers, agronomists, looking at kind of the farm scale or even the field scale, what goes in terms of nutrients, and it takes into account rainfall, climate. So that's one. Another would be SWOT, and I know many people in the room here are pretty well versed in SWOT, so that's the Soil and Water Assessment Tool. And this has often been used for planning total maximum daily loads, looking at more of the watershed scale of what's going on with water quality. And then there are other tools that are maybe more focused on long-term regional planning. SWOT, again, can be one of those tools. ModFlow, if you're interested in groundwater, is another example here, and we're very lucky here in Dane County to have an updated ModFlow groundwater flow model. So I'm just presenting these just because our modeling suite is kind of grabbing the bits and pieces from these different models and incorporating them into one kind of one set of models to account for nutrients and water and the effects of groundwater. And to dig a little bit more into some of those previous efforts, there's actually, we're not the first group to do scenarios in the Yahara. I think I saw Steve Gaffield come in earlier. So Montgomery and Associates and the Yahara Clean Project, they came up with several scenarios of the Yahara back in 2011, looking at different best management practices, what would happen if we reduce manure to certain levels. And so we're kind of already at this point in 2011 where we're starting to think about what could our watershed look like. And so we're extending that thinking and creating more integrated scenarios, looking at not just best management practices changing in the future, but also climate, policy, all these different drivers coming together into 4 really contrasting scenarios. And like I said, our modeling suite kind of pulls from several of these other models that you might already be familiar with. And it's made up of 3 core sets of models. So the first being AgroIBIS. This is this dynamic vegetation model. And we break up the watershed into a grid, and each grid cell, AgroIBIS is working on that independently. And you can think of each of those grid cells as a vertical soil column. And you have inputs of climate going into that grid cell. You have inputs of land cover and land management that might change on an annual basis. And you also have nutrient applications going on to that grid cell. And below the surface, you have a lot going on where we're accounting for flows of water, nutrients, carbon, and also accounting for, if the water table is shallow, how that might impact what's going on in the soil and impacting what's being produced on the ground surface. What's coming out of that model is, at the surface, we've got runoff, which of course includes water, but it also includes sediment and phosphorus. And at the bottom of that soil column, we have drainage of water and drainage of nitrogen. What happens to that then is shoved off onto the next model, which is our routing model. And this is where the interconnectedness of the watershed comes into play, and we force water to move downstream through the stream network and on through down the 4 Madison lakes. Then finally, our last model is more of an empirical lake water quality model that takes that phosphorus from the stream network and uses that as a predictor of lake water quality. And we can get an indication of even what the Secchi disk depth would be doing as far as phosphorus load is concerned. And so there are some similarities with SWOT. If you are familiar with SWOT, we have added a few new capabilities that might be unfamiliar in terms of soil hydrology. And Missy's going to spend a lot of time on the upgrades that she made to the model in terms of phosphorus cycling, which is based on Surfos that Pete Vadas created. And the overall goal, though, here, remember, is we're not just looking at best management practice changes in the future. We're looking at kind of holistic changes, and we're marrying these qualitative narratives with more of a quantitative look at what are the consequences of what's going on in the narratives. And I like to call that integrated scenarios. So a quick little synopsis of, Jenny mentioned how the scenarios were created real quickly, but we started with the narratives, of which a lot of you in this room actually played a role in creating some of the themes of those narratives when we were first starting this project. And then those are translated into elements that a model can understand, and that gets whittled down into 3 categories: climate, land use, land cover, and nutrients. So each of those stories are going to vary in terms of the climate and the land and how many nutrients we're applying to that landscape. From there, the model is now familiar with what's going on in the scenarios, and it can crunch through all of its computations and output many different ecosystem services, of which we can kind of summarize and get a rich picture of what's going on under each of these different scenarios. And so today I'm going to give a real brief summary of 6 of these ecosystem services and kind of concentrating on the first 5. So food production, biofuel production, surface water quality, flood regulation, freshwater supply, and I'll just show one figure of groundwater quality, but concentrating on the others. And again, we might all have a favorite of these 6 that we like to concentrate on, but the goal here is to kind of look at all of these holistically and recognize that other people might have different priorities as well. Hopefully everybody at this point is fairly familiar with the 4 scenarios. We had a documentary come out and we've got a lot of material online, but just to get us all back in that same frame, I'm going to give you a quick little rundown of each of the 4. So the first one is nested watersheds, and this is where government intervention is kind of the dominant force. And the landscape ends up looking a lot of perennial grasses being grown for biofuels. The second scenario is abandonment and renewal. So during the 2020s and 2030s, we have an intensification of agriculture, and in the 2030s, there's a disaster that leads to depopulation, and the landscape largely becomes feral, and we have a lot of unmanaged grassland across the watershed. Accelerated innovation, this is where technology is the main driver of change. We see a massive growth in different businesses, tech businesses. Urbanization is the largest in this scenario, but the rest of the landscape, the agricultural part, is dominated by corn and soy, which is feeding this new industry, creating synthetic meat and dairy products. And then finally, the connected communities scenario is where values are the main driver of change towards sustainability. There's less consumption of meat and dairy and energy, and green spaces dominate the landscape, as well as pasture and vegetable production. So I think that was maybe the quickest I've ever explained those 4. The climate also varies in each of those 4 scenarios. A quick little synopsis of each. You can look at air temperature on the left as kind of an indicator of the severity of climate change. So the most severe being that abandonment and renewal scenario, and the least severe being the accelerated innovation, with the other 2 kind of in the middle, but all spanning kind of the range of plausibility that we have gotten from the IPCC climate projections. And then annual precipitation, the first few decades kind of follows this trend of an increasing amount of water, and a few of them get drier by the end of the scenario, just so we can see some contrast, and it's still, again, within the realm of plausibility. So into the results, I'm going to go through each of those 6 here in sequence. And food production, the main lesson here is that while climate does have an impact on yields, the main driver of actual food production is going to be the choices that we make of what to grow on the landscape. So I put up all the plots of the different crops that we would grow that would ultimately go towards food production, but I want to just make the point that that's not what is giving the full picture. We need to whittle that down into something that makes a bit more sense to summarize, and how I chose to do that is to convert all of that food production into human food calories so that we can at least look at one common metric across the 4 scenarios. And before I do that, I just want to give a quick little methods of how that was done. And so the ultimate source of our energy in terms of food comes from the sun. It goes to these different crops, and then we have a few choices about how that then gets to our dinner plate. The first is just the most direct. We can eat corn, soy products, or wheat and veggie products directly as food, or we can use them as feed in our livestock system. And that is the common picture of what is done in the Yahara today, primarily the one on the left being dairy. And then ultimately those turn into food products that we can eat. We have actually a third pathway that we have created as part of the scenarios, which is synthetic meat and dairy in the accelerated innovation scenario. And so we had to come up with a method for converting the energy from crops for that into the energy that we ultimately get in human food. And the main message here is that these pathways, the red and green over here, are more efficient than the pathways through the livestock system. So that is the main driver of the total food calories that we receive. So for all these different indicators, just to give you a heads up, I'm going to show what they're doing through time on the left, and then more of a what's going on the last decade of each of the scenarios. And by the end, for food production, I'm going to give you an indicator of how many people can be fed based on what is produced in the watershed. And here we have the gray bar representing what we're creating today. And as a reference, the Yahara population in 2010 is 370,000 people, and we are producing, at least in terms of calories, food for 2 Yaharas. But that changes according to the different scenario that you pick. Accelerated innovation, the one with the synthetic meat and dairy production, is the winner in terms of calories produced because of that highly efficient way of converting energy. The other scenario that is second place is the connected communities, which is more emphasizing vegetable production. So these are the main drivers of how we're getting these ultimate values. Bioenergy production is largely similar. It's, again, going to be impacted by climate to a certain extent. The dry years are going to lead to lower yields, but it really is driven by what we choose to grow on the land and how we convert that into energy in this case. So our 3 major feedstocks for bioenergy are corn, soy, and we're calling it hay here, but this is the perennial grass biofuel that is a large player in nested watersheds. So when we look at that as a final result, we see, again, the gray bar indicating what's going on today. And the metric I use here is if we all had 1 car to use as a population, how many miles could we drive that car based on 1 year's production? And today, we can drive about 13 million miles. Fun fact. Nested watersheds turns out to be the winner in terms of the 4 scenarios because of that emphasis, that policy emphasis on creating a biofuel landscape dominated by perennial grasses. The other 3 scenarios, that's just really is not a major emphasis of what we want to use the watershed for. Freshwater supply is up next. And the indicator I'm using here is, as I explained earlier, we have drainage coming out of these vertical soil columns across the watershed. And that's a pretty good proxy of groundwater recharge. And when we look at the average amount of that drainage across the watershed, even though several of the scenarios get wetter in terms of precipitation, drainage never gets higher relative to today. And that's because we have a warmer climate. There's more water being used by plants and evaporating off of the surface. And so that leads to less overall recharge. And the implications of that, you can tease it out a number of different ways. The way I chose to tease it out was I used that modified amount of drainage and linked it to the ModFlow model that we have for Dane County and ran it and determined what was going on at all of the private wells that we currently have today. So these are the shallow wells that a lot of people in our watershed depend on for their water supply, and they're kind of the first line in terms of impacts. Our deep, high-capacity wells where we get Madison, our city of Madison water, they are so deep that impacts of climate change are going to be very buffered. But these shallow wells might be more of a concern. And so the average of the drawdown at all of those private wells across the watershed for the driest scenario is about 4 meters. And that could definitely mean that some of those wells end up going dry by 2070. So this is largely driven by climate. There's not a ton we can do in terms of making our landscape more drainage friendly. In urban areas, we can certainly do BMPs, but overall, this is a climate-driven phenomenon. Then on to flooding as our next indicator. I'm going to start with kind of the biggest flood that we saw across all 4 scenarios. That's in abandonment and renewal in the year 2031. And you can think of this event as very similar to what happened in Lake Delton in 2008. And it actually turns out Ken Potter and David Liebel, if you're familiar with their project looking at storm transposition, they transposed that storm from Lake Delton and put it over the Yahara watershed, and we ended up getting results very similar to theirs. And what we see is a very wet isthmus for several weeks during this event. And I don't mean to present this worst case scenario of all 4 of our scenarios as kind of an alarmist view of things, but it's certainly, while it's a low probability event, it's certainly within the realm of plausibility and something to keep in mind when we're looking at all these different outcomes. The other way of doing flood regulation is not to just look at the biggest event, but what are each of the 4 scenarios doing in terms of flood severity. And the metric I'm using here is a little obscure, so let me walk you through it. On Lake Monona, if you're familiar, once it reaches a certain level, the county will come out with a no-wake order, and you cannot drive your boat fast because there are consequences to the shoreline in terms of erosion and flooding. And I'm using that as kind of a threshold. So that's the red line on the left-hand side figure. And once you cross that threshold, I'm going to keep track of how much above that threshold and for how long. So I'm going to quantify the area above that line essentially. And I'll do that for the entire time period of the scenarios. And I'm presenting that sum area here on the right. But without getting too much into the details, you can just think of it as flood severity. The gray bar again being the historical look of this flood severity metric, and I'm using the same number of years for a comparison. So this is 1957 to 2013, so a relatively small amount compared to all of the 4 scenarios. So even in the driest scenario, we're still getting quite a bit of these large flooding events occurring. The final one, surface water quality that I wanted to touch on, and Missy's going to go into much more detail on this, but the output from our lake water quality model, again, is water clarity, and Secchi depth is what we're using as that indicator. And in the first few decades, we noticed that all 4 scenarios decline in terms of water quality as we see more rainfall and not much changes on the landscape. But by about 2030, 2040, we start seeing major land cover changes in each of the scenarios. And all of those changes actually benefit water quality in different ways. And so by the end, in the final decade, here is our comparison again, today versus all 4 scenarios. And the winner in terms of Secchi depth is actually abandonment renewal, but nested watersheds is right below it. And again, these are the other ones like drainage and flooding were very climate driven. This is also climate driven, but there's a little bit of landscape management that comes into this as well. And I'm going to let Missy focus a little bit more on some of those nuances here in a second. But when we put all of that together, this is all that I presented to you in the last 5 to 10 minutes. And instead of focusing on each one individually, if you look at them all together, the thing to notice is that there's not one perfect ideal scenario. There's always going to be a trade-off among these 6 different indicators or services. And another way to show that is with what's called a radar diagram. And the way to read this is the farther out to the edges you are, kind of the better off you are in terms of ecosystem services. And you'll notice that, again, there isn't one clear winner where we're maximizing those services across the board, but you'll see trade-offs among the different services. And so I would argue that sustainable management of all of these different services requires considering all 6 of them together holistically and making sure that we're transparent in how we measure them and communicate them among the differing communities in our watershed. So with that, I'm going to give it over to Missy, and unless we want to do questions now on this, or do you want to save them to the end?
We have time for maybe one or two concise questions for Eric. That's a lot to take in.
And we can talk about technical details in the work groups as well. But
all right.
Okay.
All right, good afternoon. Well, thank you all for coming. My name's Melissa Motew, but everybody calls me Missy, and so can you. So Eric gave us a nice overview of the model results as a whole, and right now I'm going to just dig into some key issues related to surface water quality specifically. These issues have emerged from our research findings, both the scenario simulations, but also some other studies that we've been conducting. So I really just want to focus on some of these key issues on water quality with the hope that these topics are going to be relevant to researchers and managers and policymakers alike. So there are 3 issues that I'd like to touch on today. So the first is legacy phosphorus, or legacy P. What is that? Why should we care about it? What could be done about it? The second topic is climate change, namely changes in precipitation that we're expecting in the future. What does that mean for water quality? And then the third topic is invasive species, how their effect on the food web is so important and why we really do need to think about prevention. Okay, so to begin, legacy P. So what is that? So legacy P, if you haven't heard of it, it is phosphorus that builds up in the environment over time. So it's building up in soils and sediments. And this happens mainly because we humans are applying phosphorus in amounts that exceed the rates at which we're removing it. So this diagram here tries to illustrate the typical inputs and outputs of phosphorus to the soil system in an agricultural area, say a farm. So in this system on a farm, the largest inputs of phosphorus to the soil system are typically manure and fertilizer, and the largest outputs of the system would include what the crops take up and then what we harvest away. These other fluxes coming into and out of the soil system, such as atmospheric deposition, losses in runoff, losses in leaching down lower into the ground, those fluxes are generally much smaller than what we're applying and what we're removing. So for example, maybe a typical farm in Dane County, we might have a farmer applying 30 kilograms of phosphorus per hectare in a given year, but we might only be losing 1 kilogram of phosphorus per hectare to runoff. So it's a really small amount compared to how much we applied, but the problem is that 1 kilogram might be more than enough phosphorus to cause eutrophication in the nearby surface waters. So it's useful to think about how the amounts of phosphorus that we're handling on the landscape really are much, much greater than the amounts of phosphorus needed to cause harm in aquatic ecosystems. And similarly, it's helpful to think of the fact that it's easy to build up phosphorus in the soil if we're not balancing that P budget very precisely. So if we're applying 30 kilograms of phosphorus in manure and say we're removing 29, well, that's leaving 1 kilogram of phosphorus here to build up over time. And over the years, you can see that these amounts can grow very quickly. And if you're a fish in a nearby stream, right, that 1 kilogram poses a pretty substantial risk. Okay, sorry, I'm managing 2 devices here. Okay. So we conducted a recent study on the effect of legacy phosphorus on water quality in the Yahara lakes. So in this study, what we did was we ran 5 simulations using our models, looking at 5 different amounts of legacy phosphorus stored in soils and streams, ranging from a low amount to a high amount. And then this medium case here would correspond to our best estimate of what actual soil phosphorus would be. And we looked at the effects on several different indicators of lake water quality, 2 of which are shown here. This is direct drainage load to each of the 4 lakes, and then summer TP concentration in each of the 4 lakes as well. So overall, what we found was that the effect of legacy P is indeed significant on lake water quality. So for example, in the case where we reduced legacy P from recent historical conditions down to this low case, which is about a 50% reduction, we saw in Lake Mendota direct drainage loads reduced by about 35%, and then TP concentration in Lake Mendota decreased by about 25%. So the effects are significant. And not only are the effects significant in magnitude, but they are also persistent. So we ran 30-year simulations with these different treatments of legacy P, and the effects of those different treatments were persistent over the course of 3 decades. So we know that phosphorus moves very slowly through the environment, it sticks around a long time, and it can be affecting our water quality for multiple decades. So we should keep in mind that in any given year, a lot of the phosphorus that's reaching our lakes is actually coming from legacy sources, not just what we apply this year, but actually what we've applied in past years. Okay, so another key point I'd like to draw your attention to that's related to legacy P is dissolved P. So when we talk about P transport, we typically refer to 2 forms of phosphorus. So the sediment form, which is phosphorus that's attached to sediment soil particles, and then the dissolved form, which is dissolved in water. You can't see it. It washes right away with runoff. So sediment P is often thought to be the dominant form that's mobilized in watersheds. But in the Yahara, and I suspect in other watersheds in Wisconsin, dissolved P actually makes up a large fraction of the total loads reaching the lakes. It's about 50-50 in the Yahara. And the reason for this is likely due to the fact that we have lots of manure being handled in this watershed. Manure is rich in DRP. We also have very high soil P concentrations throughout the watershed, and high soil P is associated with dissolved P loss. So from a management perspective, I bring this up because many conservation strategies tend to focus on erosion reduction. So for example, reduce tillage, vegetative buffers, cover crops, and so forth. These strategies can be really good at reducing sediment P, but they don't necessarily reduce dissolved P loss. And in fact, no-till practices have actually been associated with increases in dissolved P loss, because with no-till you have to apply your nutrients to the surface of the soil and it accumulates there. And this is one of the unintended consequences. So we saw losses of dissolved P play an important role in the scenarios. Since several of our scenarios featured conversion of the landscape to a perennial system of some kind, either grassland or a pasture, we saw reductions in sediment P, but we didn't see the same kind of reductions in dissolved P, and that was pretty interesting. So for example, in abandonment and renewal, this is showing by decade how much phosphorus yield was coming off the landscape on average across the watershed, coming from these different sources. So in the dark blue, this is sediment phosphorus, and then the yellow, the green, and the lighter blue are dissolved forms of P coming from these different sources, so the soil, from fertilizer, or from manure. So in abandonment and renewal, the first half of the scenario, we have intensification of agriculture, lots of chemicals, lots of nutrients going on. And then we have the disaster happen, and then you can see the grasslands come in, we have a reduction in erosion and sediment P, but we don't see the same kind of reduction in dissolved P. And the reason is because we have such high soil P concentrations accumulating in the first half of the scenario, and what we're seeing here are the legacy effects of that. So again, we're seeing legacy phosphorus effects lasting over multiple decades, and suggests that it could go on for even longer into the future. So the bottom line here is that reducing erosion may not necessarily reduce dissolved P losses. Okay, so what can we do about legacy P? And I don't have the answer, but maybe we do together. I don't know. But first of all, just something to keep in mind is the need to think about balancing the P budget. So this means not applying more than we're taking away, right? It is a mass balance problem ultimately. Also, we should think about removing what's already there by crediting the phosphorus that's already in our landscape. So does this mean we need to ramp up our soil testing, so that we can identify the places on the landscape where there are hotspots and need intervention? Does it mean we need to do more soil testing on a finer scale so that farmers know on their land where to be applying and where to not be applying? So some possibilities there. Balancing and crediting may not seem like a new idea. They seem pretty straightforward, but it may in fact represent some kind of a shift in management is needed, because many management strategies are focusing on containing phosphorus on the landscape, right? Blocking it, not letting it get off of the field. But what our research is suggesting is that containment strategies are going to be extremely hard or extremely challenged. It's really hard to keep that phosphorus in place because we're handling so much. There's really very little room for error. So reducing the supply is a solution that would address the root of the problem. And when I talk about climate change in just a minute, you'll see that it'll probably become even more of a problem. And then as far as this last point on minding dissolved P, this is something that's receiving more and more attention from what I've seen. For example, in the Lake Erie Basin recently, increased DRP loads to Lake Erie have been linked with some of these colossal algae blooms that have been taking place. So despite a lot of management interventions taking place in that basin, they were seeing some unintended increases in DRP loads, and that's been part of what's been causing these catastrophic algae blooms. And we made an effort with regards to dissolved P to use the best P loss modeling tool that we could find, which was SURFOS, which was written by Peter, who's with us today. He's with USDA. And we certainly encourage others who are working with models out there in the research community to take advantage of these new advancements that SURFOS and some of the SURFOS has a few other products associated with it now, to take advantage of these, because we're certainly lucky to have this kind of science being developed right here in Wisconsin. So climate change. So with climate change, we're certainly expecting that increases in precipitation and especially increases in storm intensity are going to impact water quality. So surface runoff, of course, is the main physical mechanism that delivers phosphorus from land to water. And the Yahara watershed is particularly sensitive to extreme rainfall events. So we're expecting this to not be so good for water quality. And we did see a dominant influence of precipitation in driving loads in the scenarios. So for example, I'll pick on abandonment and renewal again. Eric already showed you this. This is just the annual precipitation time series for the 4 scenarios. And you can see we have this period in abandonment and renewal in the 2030s where there are some really severe floods happening. And right corresponding to that in loads to Lake Mendota, we have huge spike here. And this is topping out near 70,000 kilograms of phosphorus per year, which is more than double what we see in the recent historical record. So as you might imagine, legacy phosphorus and climate change, not such a good mix for water quality looking ahead. We did conduct a study recently looking at how these two drivers might interact. The question being, does the effect of storm intensity depend on how much phosphorus is out there on the landscape? The answer, unfortunately, is yes. The effects of storm intensity do seem to be made worse when the supply of phosphorus is high. So specifically, this relates to phosphorus stored in surface manures, and it relates to the dissolved P that's being lost from that manure. So these plots try to illustrate this, what we did in this experiment. So we used 2 different treatments of rainfall intensity, low and high, and then 2 treatments of phosphorus supply in the landscape, or legacy P, you can think of it, low and high. And then we crossed the 2 treatments of rain intensity with the 2 treatments of P supply in a 2x2 factorial design, giving us 4 possible combinations. And then these data points here represent the means of those 4 simulations. And we looked at TP concentration in runoff, so the field scale, and then at the stream scale, and then also at the lake scale in Lake Mendota. So what we see is that the effective rain intensity is higher when the supply of P is high. And that's indicated by the fact that these dashed lines are not parallel. If there was no dependency, no interaction, as we say, then these lines would be parallel, but they're not. So this means that ultimately surface manure appears to be particularly vulnerable to extreme precipitation. Okay, so implications of climate change. Increases in rainfall, increased storm intensity are going to make containment harder. So again, strategies that reduce the amount of phosphorus on the landscape would address the root of the problem and may have protective benefits against climate change. So excuse me if I sound like a broken record, but reducing that supply does seem to be the holistic way to address some of our water quality problems. I mentioned manure injection up here because this could be an intriguing management possibility. So with manure injection, what you're doing is you're physically putting the manure into the ground, so it's not on the surface, it's not as vulnerable to rainfall, those extreme events that I was just talking about. It's compatible with no-till. So no-till is effective at reducing sediment phosphorus loads. But the problem is with no-till, you get this accumulation of surface nutrients and you can increase your dissolved P losses. So perhaps this management strategy could allow farmers to reap the benefits of no-till, but also mitigate this vulnerability of manure sitting on the soil surface. And then last takeaway point regarding climate change, we would encourage people who are conducting modeling studies or any kind of analytical studies looking at watershed management strategies, whether it's TMDL planning or what have you, to really consider future climate conditions in your analysis. Because as we move into the future, current and past climate is just going to become more and more relevant. And there are data sets out there. There are downscaled climate projections. We made use of some of those. And there are techniques of modifying past climate records to simulate the future. So we are proponents of incorporating that into analysis and studies of water quality. And we'd be happy to talk, our team would be happy to talk with anybody about data sets or anything along those lines during our breakout groups. Okay, last topic, invasive species. So changes in the food web, such as those that are caused by invasive species, can directly impact water clarity. So this is a diagram from a paper led by Jake Walsh and Steve Carpenter and others, showing how food web interactions affecting the native zooplankton Daphnia, shown right here, can have a direct impact on water clarity. And this is kind of a timeline showing what has happened over the past 3 to 4 decades. So in about the late 1970s, we had a situation where Daphnia had a lot of predators. And so the population of Daphnia was rather low and water clarity was correspondingly low. A biomanipulation exercise was conducted beginning, I guess, in the late 70s and then progressed again in the late 80s, where the populations of these larger piscivorous fishes were increased, which helped keep Daphnia's predators in check. Daphnia were able to rebound, and then water clarity responded, got better. Recently, we've had an invasion of the spiny water flea in Lake Mendota, and the spinies happen to eat Daphnia. And we've seen a direct impact on water clarity as a result of this invasion. And this invasion is still ongoing, and from year to year, we're still learning how this is playing out. So there are a lot of unknowns with respect to invasive species. So given Daphnia's important role, it makes sense then that water quality outcomes will depend on whether or not Daphnia are present. So our water quality model generates estimates for either case. It will assume either Daphnia are present or they're not present. So here's an example of what the presence or absence of Daphnia could mean for water quality. So this is a plot here on the left of summer Secchi depth for each of our 4 scenarios in Lake Mendota, and this assumes that Daphnia are indeed present in the future. On the right, it's the same plot, except we're assuming that there are no Daphnia. Maybe there's some kind of invasive species that ate it, or there's some other alteration of the food web that affects Daphnia in a negative way. So the shapes of the plots look the same, but you'll notice the axes are different. So in fact, Daphnia increases water clarity by about 1/2 meter. So we can thank that little guy there for about 1/2 meter of water quality. Right there. So 2 meters Secchi depth is one of these trophic thresholds. Let's see, if it's greater than 2 meters, then it's considered mesotrophic. If it's less than 2 meters, it's considered eutrophic. Yeah, thank you. Right, so 1/2 meter from Daphnia. So one interesting thing to note is that if you look at the scenarios, we do see improvement in water clarity over the course of the scenarios, something like 0.4 meters from beginning to end. That's like 60 years of massive landscape change. Land use, land cover, land management, nutrients, government, world upheaval. Everything is taking place in these scenarios, and we only got 0.4 meters of improvement. And yet Daphnia gave us 1/2 meter. So the implication here is that by preventing invasive species, maybe that can buy us as much water clarity as can be achieved through massive changes on the landscape. Food for thought. So some takeaways on invasive species. So preventing and managing for invasives is not a new idea, I'm sure, to this audience, but it's important, as I hope I've been able to demonstrate here, and arguably, maybe, possibly, more feasible than relying on landscape change. Who knows? That's not to say that preventing invasive species is easy to do, because changing human behaviors, as we know, is quite difficult. We've seen success in the past, like with the biomanipulation experiment, when water quality managers work together with fisheries managers. So that could be an important consideration in this regard. And then lastly, it's important to expect the unexpected when it comes to invasions. The spiny and the Daphnia are a good example of a very unpredictable invasion with real consequences for water quality. But we don't know what the next invader is going to be, and we don't know what the impacts of that will be. So for example, the zebra mussels have been detected in the Yahara lakes, but we don't know what's going to happen with that just yet. So we are definitely keeping our eyes on it. But we know that we want to protect and support the benefits that the food web provides. And that's all I have. We do have another talk coming up, one more. Do we have time for any quick questions? Maybe 1 or 2. And we can also discuss things in small groups and happy hour. Yes. Yep. Yeah, with manure injection, right. So that's true. Manure injection doesn't really address the mass balance issue because we're still injecting it in there. But manure injection, maybe it's more of a compromised approach because, just halting all manure applications or reducing them dramatically is obviously really challenging to do. It's not entirely realistic. So maybe something like manure injection is a way to mitigate some of these, unfortunate phenomena like, the vulnerability of having, manure sitting on the surface of the soil. It could be an effective way so that farmers can, it's kind of a point approach, right? So we're really targeting, we know that no-till works for certain aspects of protecting water quality, but it has this weakness. So can we address this weakness? So I don't know, maybe other people in the room are more familiar with the technology and its promise. Maybe it's too expensive. Maybe there are some barriers or challenges there, but just it was just an idea that I had. Yeah. Yeah, in the back. Yeah, I would have to punt that question to our limnological expert, Steve, in the back, because I'm definitely not qualified on that. Sorry, Steve. Okay, thank you. Next, I'm going to pass the baton to Adena Rissman, who is, let me get your slides, Adena. Here you go. So if you want, do you want presenter notes?
Sure.
If you do, then you have to do 2 machines at once.
Okay, then no.
Then no, then just worry about that.
Okay, great. Excellent. Well, good afternoon. My name is Adena Rissman. I'm an associate professor of the human dimensions of ecosystem management here at UW-Madison, and it's been my pleasure to work with the water sustainability and climate team for the past number of years. And today I want to present just a couple of snapshots of some of the social science work that has gone on as part of this bigger project. So we've been talking about the very long term and then in thinking about scenarios, and now I want to connect it to some very short term ideas about how people are responding and perceiving issues in the Yahara watershed. So I want to present results today of a survey of participants in the survey were residents of Dane County, and we surveyed 1,100 people, and this was in the fall of 2015. And we received about a 50% response rate, which is pretty good for a male survey. And what I want to show you is 2 types of results. One is how people weighted the importance of different kinds of ecosystem services, the kinds of services that are being modeled in the scenarios. And then secondly, how they responded to a variety of different water quality policies. So first, ecosystem services responses. We found that of all of the different ecosystem services, which are benefits provided by the environment to humans, that water services ranked most highly. So we asked people, how important is it to you that this service be provided in the region? And water for households, not surprisingly, drinking water and water for showering and laundry were the highest items there. But just slightly lower was clean lakes and rivers for fish and wildlife and reliable supply for lakes and rivers. So clearly water is very important, and this was really across the board. We did a lot of statistical analysis to look at trends. We oversampled rural in the region, so we would have respondents who are both rural and urban, and this is both Yahara watershed and other parts of Dane County outside the watershed. And while we found some some predictors of varied levels of support, really across all the different demographic groups in the watershed. The importance of water was very high. We also saw a lot of importance of forest and grasslands and recreation. We also saw pretty high support, although a little bit lower, for agricultural production. Farmer livelihoods, out of everything we asked about, agriculture, farmer livelihoods was the highest. And fruits and vegetables was the next highest, followed by ag products for local consumers and dairy products. When you get to grass or pasture for livestock, corn and soybeans for livestock, and ag products for non-local consumers, which is a lot of what we grow here, the support was relatively lower. And when you get to biofuel crops, there was much less feeling of importance that people reported. Yeah. Oh yeah, thanks. So this is the mean score for all the respondents. So a 1 is not at all important, and a 5 is extremely important. And then this is just the mean. So somebody who, or an average for the top one, clean and safe drinking water, was an average score of 4.9. So basically almost everybody is ranking that as a 5. Extremely important. A 4 is very important. 3 is somewhat. 2 is slightly important. Thanks. We also asked about rural character. That was somewhat to very important, and also asked about flood control, which was very to extremely important overall. And we grouped these by color into the Millennium Ecosystem Assessment Groups, which is a global effort to try to understand different kinds of ecosystem services, those that are cultural in red, provisioning, so provisioning direct services, regulating services in purple, and then supporting services in green. And we found that those groups are not really how people think about what is important to them, that they're really making distinctions based on other kinds of factors. Our next step with this is to look at how these different importance scores play out across the scenarios, to look at how different groups of people who value different things kind of win or lose in the different scenarios over time. So I'm going to move on to the next question that we asked about, which is about policy support. So overall, let me just talk you through how to read this graph. We asked about a number of different policies listed over here on the left, and we asked about many of them for farms and for lawns. And we asked, would you support or oppose, say, a utility credit for lawn care owners or those who manage lawns to reduce runoff? They were all about reducing runoff from either farms or lawns. And with lawns, we specified urban lawns in particular. Oppose is over on the left, and support is over on the right. And these percentages sum up the total of both of the greens. So somewhat support or strongly support on the right, somewhat oppose or strongly oppose on the left, or neither oppose nor support in the middle. So you can see overall there's very high support in the watershed for a variety of kinds of water quality policies to reduce runoff. And we divided these into carrots, things that are more of incentives, or sticks, things like regulations and taxes. And overall, probably not surprisingly, people prefer carrots. And so you can see utility credits being the highest level of support, certification programs, tax credits for farms, followed by some of the more stick measures, tax penalties for farms, regulation for lawns. But even so, the majority of respondents supported all of these options. Technological solutions, a little bit surprisingly to us, was the least supported, although still more supported than opposed of these policies. It could be that we called out, in a couple of these, we called out the role of public funding, particularly in the question. And so maybe that's why technological solutions had a somewhat lower score. The thing that was overall opposed was the question where we said, what if we rely only on voluntary practices without government involvement. And for farms, the majority of respondents opposed that, that policy option. And so you can see 52% somewhat to strongly opposed, whereas 26% somewhat to strongly supported that option. So there's a lot of talk these days about what some of our potential approaches might be for getting to the water quality solutions that many of us want, and that really nearly everybody wants to have clean water. The question is, how do we get to it? And we hear a lot about, well, should we have increasing regulation and taxes? Should we have regulatory reform in which we're moving away from a government role? And so this, I think, can help provide something of a take on how people here locally feel about it. For our research purposes, we then went another level to look at what factors predicted these scores. And so I just want to review those quickly here. And I did have pretty graphics that are not showing up. So anyway, just black and white, that's okay. So we looked at a few different things in particular and whether they predicted these support scores. One is values, and here for values we looked at cultural worldviews. And one of the important ones is whether somebody is more communitarian or individualist. Okay, that's weird too. And another is the role of self-interest. So whether somebody has an agricultural occupation or whether they have a lawn themselves might predict, that role of self-interest might also predict their support or opposition to these policies. And we found that worldview was a much more significant driver of policy or support or opposition than self-interest. And it's something that I think in a lot of day-to-day discourse, we might think, oh, people are mostly driven by their self-interest. But we did find something of a role for self-interest, but really it was these broader values that are really entrenched and difficult to change that are driving people's ideas and their support. We also found here that regulatory approaches were somewhat polarizing. When you think about people with different worldviews, communitarians, now remember, everybody likes carrots better than sticks, but communitarians only like sticks a little bit less. But individualists who think there's too much government involvement in our lives and people should be left alone more, really liked sticks a lot less than carrots, right? So that makes sense. So some of the broad take-home messages here are that water quality is highly valued, both among urban and rural residents of Dane County, that residents supported agriculture, especially farmer livelihoods, local food, and fruits and vegetables and dairy, were less connected to something like biofuel crops. And one of the reasons this connects back to the scenarios is because in the scenarios, we're making trade-offs, but residents themselves, when they think about what's important to them, they don't automatically make that trade-off. Everything can be important, and you can want a little bit of everything, regardless of whether you can really have all those things at the same time in the same place. We also found water quality support was high, and that support was higher with a positive view of government and society, higher water quality concern, and no direct self-interest. And that regulatory rollback that removes the role of government may not be that widely popular, particularly in a place like Dane County. Another thing that we found that was interesting to me is that there was a role for self-interest. We found that people with an agricultural occupation were less likely to support regulation of farms, but actually somewhat more likely to support regulation of urban lawns. Urban lawn owners didn't really seem to have a perspective, one way or the other on farms. So a conclusion from this is that outreach, as we talk about different policy options, should seek to align with diverse worldviews. And a way to do that, to appeal to individualists, is often to appeal to a business interest, an entrepreneurial interest of clean water, and to avoid things that can serve as reactants that people react against automatically. So I'll stop there.
Any questions specifically for Adena?
Yeah, I'll just take any clarifying questions about the data, and then we have time now for a discussion that will open it up.
before we go into our breakout groups. And maybe before I do that, I realized I got so excited about the presentations that I forgot to tell you some things. But just so you know, there's food and coffee in the back if you ever need it. You all received a handout that has some of the key messages from these presentations on it. So that's what that packet is. We are video recording this presentation so that if you want to look back at it or send it to colleagues, it will be available. And that finally, just so you know, that from the discussions that we're going to have later, we do intend to create a summary of what we all talk about. So you will, there'll be a product that comes from this. And how it's going to work from here on out, we're going to have about 15 to 20 minutes to have Q&A specifically about the presentations, and then we're going to break into small groups to have smaller conversations talking about the implications of this research and what it might mean for the work that we're all involved in. So that's just sort of a snapshot of what the rest of the afternoon looks like. So I guess if there are any questions, I have, just so that we can get your question on the video, I have a microphone here, and I'm going to race to you and give you the mic if you have a question. Yes.
Thank you. This is for Adena. Back in 2010, the Public Policy Forum in Milwaukee did a similar survey of participants in the Milwaukee River watershed. And one thing that came out from that, which I would be interested in knowing if you have any idea, if you can translate the information that you have into a similar result, is when they surveyed people on their responsibility to future generations to protect the region's water resources, even though there was a lot of support for improving water quality, et cetera, only about 4% of respondents indicated that they felt like they had a responsibility to future generations. And considering that you also have that two-generation view anyway, wondering if there was any research on that, or if you have any anecdotes that you can share that might kind of help us consider that going forward in the Yahara watershed.
That's an interesting and very low number. Did everybody hear the question? Yeah, because it was on the mic. Okay, great. So we didn't ask that particular question, and it's something that I would actually expect in landowner surveys. Most landowners are ranking that much higher in terms of a stewardship responsibility for future generations. Now, it depends on exactly how it's worded. If it's just narrowly about water quality, that's going to be lower. But if it's a broader stewardship responsibility or ethic, that does tend to be higher. So yeah, I think having abstract support is going to be a lot higher than actually being willing to make any kind of behavioral change. And so to the extent that people are answering it thinking, would I have to actually change something about what I do? Yeah, I would expect that number to be lower.
Hi, this is a question for Eric and Missy primarily. On the legacy phosphorus issue, it seemed from the documentary and from some of the stuff you talked about today that with increased runoff, legacy phosphorus becomes a very, very key component of this whole scenario when phosphorus loading into the system. Were there indications in your model of ways with either crop production, or primarily crop production, that you could start to mine some of that legacy phosphorus? Are there other ideas you have where you would change crop production or crop mixes in the watershed that could start to get at a negative of phosphorus accumulation?
Yeah, that's a great question. So yes, the answer is we did see ways in which crops can be used to mine down soil phosphorus. So in fact, as I don't know if you remember, but on that initial diagram showing the mass balance, so those harvest fluxes out, those are the biggest, fluxes out of the system. So that's really the best option for mining soil phosphorus down. So in the nested watershed scenario, it's probably the best example of this. We switched to a perennial landscape, but they're biofuel grasses, so they really do grow. Their yields are really quite high, and they use a lot of phosphorus, and we're harvesting it. So in abandonment and renewal, that was just a wild grassland. It was unharvested. The phosphorus didn't go anywhere. So in nested watersheds, we grew a lot of grasses, and then we harvested them. So thinking about, what crops do use a lot of phosphorus, I think corn uses a lot of phosphorus, right? But of course, growing corn has some trade-offs. Corn, is susceptible to erosion generally, whereas, say, a perennial biofuel grass is not as susceptible to losses of sediment P. So I think this is an area ripe for future, investigation. How can we grow crops in a way that can efficiently mine down those reserves that we have? Yeah.
Hi, my question mostly has to do with Eric's presentation about the ecosystem service benefits. And I was just interested in the combination of the land use scenarios versus the climate scenarios. And you didn't match every climate scenario with you kind of picked one climate scenario for each one, but yet for like water quality, for example, climate you said was one of the main drivers. So I just wonder if you've thought about how we can match our behaviors to best fit the different possible climate scenarios. And also, if you look at some of these individual climate scenarios, what was it about that climate scenario that made like water quality the best? Like in the nested watersheds or abandonment and renewal ended up with the best water quality.
We tried to have, thanks for the question. We tried to have figures that would cover almost all questions, but not that one. But yes, so the combination of climates and land use is really a critical point to make, because we did kind of marry a specific climate to a specific land use scenario. And we ended up doing a factorial experiment to try and dig into the details if you were to mix and match the climate and land use scenarios. So we didn't present that today, but I can get you that information. So for the water quality, yeah, it is really dependent on runoff. We're interested in phosphorus loads to the lakes. It's really dependent on runoff, and then runoff is going to be directly connected to the amount of precipitation. So we didn't look, oh, great. Yeah, so this is a figure of that factorial experiment, mixing and matching, but the results I'll have to give you a figure for. Overall, we didn't look at specific kind of event characteristics that would be kind of the most detrimental for phosphorus loading, like if it's a week of 3 inches of rain versus 2 days of 1 inch of rain. Those are still kind of questions that we can dig into. But yeah, overall, it really is critical to think about what climate you have in a given land use scenario, because it does make a big difference. Do you want to add anything to that?
Yeah, I would say another study that that we're working on that we haven't reported on is looking at kind of what aspects of land use and land management are important for water quality. So using this experimental setup, we looked at evaluating just the land management scenarios against the 4 climates to see which are the most robust. So where in those land management scenarios are we seeing really good practices? And what I found is that actually the biggest aspect is the mass balance, is that difference between the inputs being applied and the outputs. So this is a preliminary analysis, it's not published yet, but the mass balance in a given field is more important than the risk of erosion. That's kind of what we're seeing. So again, it's really coming back to this issue of phosphorus overabundance.
You also asked about climate change in relation to behavior. Was that right? I forget. Okay.
for the modeling, you have those 4 scenarios with, the different colored lines, and even within each model, there's a great deal of uncertainty. I'm wondering, have you done anything looking at how that uncertainty propagates through, if there's feedback in it, and then getting to the end on your output side, what's the probability that any of those results are statistically different or not? Is it 10%, 50%, 90%?
Want to talk to the sensitivity analysis?
Yeah, so we do certainly test our models. So these are really complex models. They definitely have lots of sources of uncertainty. And the main way we try to handle that uncertainty is, number one, we test our models, we validate them as best we can. That includes doing some sensitivity analysis. So it's really hard to quantify the uncertainty from so many different parameters and how that would play out. But we do try to test the sensitivity of the model results to little tweaks in the parameters. So we try to understand if the model is behaving reasonably overall. And of course, we try to validate against measurements. For our models, we're really interested in phosphorus loads being delivered to the lakes because we have a really good record of that from the USGS gauges. And that's the quantity that the water quality model needs to give us estimates of lake water quality. So we calibrate and validate for P loads to the lakes, but then we also have to work backwards so that we make sure that we're simulating correct, reasonable amounts of soil phosphorus on the landscape, phosphorus yield in the sediment form and the dissolved form, the right amounts of erosion, and everything at the stream scale. So there's actually quite a balancing act of trying to get all these different pieces of the model to give us reasonable answers. And the other thing I would mention is, because there's so much uncertainty in the models, we try not to use them in a way that's too predictive, right? We don't want to overstate anything. There's no way that we can use these models to predict what phosphorus loads to Lake Mendota are going to be in the year 2020. We can't do that. So instead what we do is we try to run different scenarios so that we can compare how the watershed system might respond to systematic variations. Of course, we did kind of throw the kitchen sink at our models with these scenarios because each scenario, as someone noted, had its own climate and its own land use and its own nutrients. But then we did eventually have to break things down so that we could kind of systematically compare what was going on across those scenarios. But yeah, uncertainty is definitely something we try to keep in mind, and appropriate use of the models, I think, is a big part of that. Yeah, not using them in ways in which wouldn't be advisable, in ways in which we'd be overstepping. Yeah.
Thank you all for your work first. I really appreciate all the work you've done these last years and really value the papers you've put out, so thanks very much. The question I have, I guess, is for those of us that are working at the county level, and we have a really excellent county staff who are doing, kind of the Lord's work out with farms. But what your papers have told us too is that despite extensive work, after 30 years or 40 years, there's no measurable improvement in water quality. And your paper, Missy, points to the issue that the conservation practices are not making, the BMPs aren't resulting in improved water quality. So I guess I just wonder, with EPA telling us we have to reduce nutrients by 50%, what's the picture? Where are we headed as a society that really loves its farms and loves agriculture, but wants to see improvements in water quality and see improvements in environment? What scale are we headed for? And are we telling farmers, are we really, kind of sharing that science with farmers in a way that they too can make change, the kind of scale change? I'm just afraid that cover crops and these sort of incremental changes that farmers are really doing and doing excellent work at are not nearly at the scale they need to be at to make these kind of changes that we need to have and to make environmental improvements. So that was a long statement, but I wonder if you thought about the scale.
So I think that gets to the heart of why we're here today, partially, is that, one of the key messages that Missy talked about is working on the phosphorus imbalance problem, and how I think it would be beneficial if we refocused or at least shifted a little bit of our focus more towards that, in addition to the ongoing efforts that we're making on BMPs, because it's important to say too that while BMPs have not resulted in an improvement in water quality, they have not been for nothing. So without them, it's very, very likely that we would be in much worse shape from a water quality perspective. So while we might want to shift our focus more towards the phosphorus balance problem, that doesn't mean we should ignore those other best management practices. But I think the question that you ask about reaching farmers, I think gathering people like this together to discuss those challenges is our goal, and one of our goals specifically today. I don't know if you have more thoughts.
I guess
Adena,
just, but have you thought about what needs to happen? You said, Missy, that you don't want to be predictive, but do you as scientists have a sense of the scale of change that we need to see in order to see these reductions? And can you articulate that?
So I think there are certainly things that we can do immediately that will have an immediate effect. And sediment phosphorus, I think, is one example that, for instance, we required cover crops across the board. That certainly would impact the sediment phosphorus substantially. Now that dissolved phosphorus is still an issue there. So that's the kind of practice that you could have a really short-term bang or an impact. But those longer-term legacy phosphorus effects, we haven't experimented in detail with how long those would actually take to impact water quality, but we're thinking about several decades into the future. So I think part of the lesson is a lesson in patience to a certain extent, which is not always the best thing to hear. But yeah, and the sooner that we start, the better off we'll be.